right, welcome to the session on functional programming in Java 8. My name is Venkat Subramaniam. I'm going to talk about functional programming in general for a little bit, and then I'll draw examples from Java 8 to see how Java 8 supports some of these styles. I'll also make certain distinctions as to a few things about functional style versus functional programming. So let's get started. Well, one of the really good things about Java is Java has evolved into supporting functional style of programming. For a good about 20 plus years, Java supported imperative style of programming along with object-oriented style of programming, but now we can actually do functional style of programming also. But why should we really care about this? Well, functional programming has been around for a very long time. It's been around for even longer than object-oriented programming has been around. And one of the interesting things about functional programming is it solves a certain number of problems that have just become imminent over the past decade or so. So one of the things is, of course, the growth of computer applications. We are seeing massive use of computer applications. We can't think of any human activity today that doesn't involve computer applications. That was not the case, of course, a few decades ago. And then, of course, when it comes to writing code, there are two kinds of complexity that every one of us deal with. One of them is inherent complexity. Inherent complexity is the complexity at the root of the application, the domain. And on the other hand, a lot of things what we deal with is also known as the accidental complexity. Unfortunately, though, while we cannot get rid of the inherent complexity, a lot of what we struggle with every single day is accidental complexity. I'm going to make the claim that imperative style of programming is inherently complex, whereas functional programming has removed that accidental complexity from our shoulders. That's one of the reasons why this is a better programming model for a lot of stuff we can do. And of course, with object-oriented programming, one of the things we quickly run into is that it doesn't quite deal with mutable state very well, and shared mutability becomes really a problem. And of course, with emergence of multi-core processors, we no longer are really dealing with multiple threads running on a single machine or a single processor. Multi-threading truly is multi-threaded, where multiple threads can run. And of course, a program that may pretend to work correctly on a single core may actually end up being broken on a multi-core processor. So how do we manage some of these issues? Well, one of the biggest problems is mutable state. Well, mutability is something almost everyone here has done, and we don't feel really that bad about mutability. So mutability is okay. What about sharing? Well, sharing is a good thing. Remember what mom told us to share. So mutability is okay, sharing is good, but shared mutability is devil's work. The minute we bring shared mutability, a lot of things can go wrong. It becomes really hard. One of them is it's a very highly error-prone code. I remember a day when a developer came to me and he said, well, this code over here is not working. Can you take a look at it? To be fair, it was not a very long piece of code. And I looked at it quickly and I said, if you send this input, it should give you this output. He said, I know, right? But it doesn't. So we both were staring at it like we are stupid. And after a few minutes, I said, wait, did you really mean to change the input given to this function on this line number 7? He thought for a second and he said, I'm stupid, and he walked away. Well, a lot of times we don't think about modifying variables. It's really hard. It becomes error-prone over time. The code is really hard to reason as well. We're struggling to really understand how this code actually works, and to explain the code also becomes very difficult. In other words, the more state change we have in code, the really hard it is to really reason with that code. And of course, wait until somebody tells you to make that code concurrent, and making such a code concurrent is incredibly difficult. In fact, one of the really big problems we deal with is the structure of the code is very different between being sequential and being concurrent, and that really hurts us to get performance out of code once we realize we have to make it concurrent. Well, functional programming solves a lot of these things, but what is old is new again. In fact, some of the concepts of functional programming really was introduced way back in 1929, 1930s, when the Lambda calculus concept was introduced. And of course, some of the first programming languages actually were functional in nature. So this is not a newfangled idea invented yesterday. It has been around for a very long time, just waiting for the industry to grow up to make use of some of these ideas. But one of the central concepts of functional programming is assignmentless programming. You may say, wait a second, are you out of your mind? How could you program with no assignments? So I want to draw a parallel to this so we can put a perspective on this. So if you really look back in time, back in the 60s and 70s, maybe even into the 80s, one of the things we really focused on is that four-letter word go to. So I'm going to say go to is to structured programming, and in other words, this is something we have been really hammered with, is not to use go tos. Let's entertain the thought just for a minute. Here I am in Java code. I'm going to go ahead and call a little thing called blah. Well, very carefully notice what this says to us. It says that error, not a statement. Just keep that in mind. Blah is not a statement. Well, I'm going to change this to go to. Well, we know that go to is evil. We shouldn't use it. Good old Dijkstra told us go tos are evil, don't use it. So I'm using go to here in Java. But when I run it, notice Java doesn't say not a statement. Instead, Java says illegal start of expression. What does that mean? Well, Java says goto is a valid keyword, but I dare you to use it. So it's a forbidden keyword. They don't want us to use that keyword. Okay, that's great, but I want to really go ahead and run this little code. I'm going to take a very simple example here. Well, we know that we cannot use goto. We shouldn't use goto. If somebody even suggests using goto, we'll frown on them. All that is great. But I'm going to go ahead and say for int I equal to 0, I less than 10. And then I'm going to, of course, just do a very trivial simple loop here, I++. In this case, of course, I'm going to say if I is greater than 5, then output the variable I. So no big deal at all. But this we know as structured programming. It's structured programming because we got nice structuring of the code. We are stacking up the code one after the other, and there is a good entry point, there's a good exit point. Hey, that's all really making sense. That's basically what we would call as structured programming. But what I'm going to do here, though, is I'm going to go to the command line and say java p minus c, and minus c is already an alias on my machine, so I won't provide that. And then I'm going to say classes right here and sample, and let's take a look at the bytecode. And what a surprise, if you look at the bytecode being generated, what do you see over there? Go to in the bytecode. Hey, wait a minute, didn't we say that in a structured program we shouldn't use go tos? Well, go tos are like matches. I'm sure everyone here has matches at home. We all use matches. But you don't go to the kids and say, kids, I'm going to go take a shower. Here are some matches for you to play with. Well, we use matches, but matches are for adults to use, not for children to play with. Case in point, goto is exactly the same. So a structured program will have goto, except that we will not have goto in our code. There could be goto at layers below. So in a very similar way, when we say assignmentless programming, we're not saying there's no assignments, period. We are saying that just like we don't use goto, we won't use assignments, but just like assignments, just like goto can happen under the hood, assignments may happen under the hood as well. So assignment is to functional programming. So this is a way to draw the distinction that goto is to structured programming like assignments is to functional programming. That is the evil part of what we are trying to avoid. Like we try to avoid goto in structured programming, we try to avoid assignments in functional programming. But a lot of times I use the word explicit assignment rather than assignment, meaning we don't do assignments, but it could happen under the hood in layers below. Well, the next thing is, of course, dealing with immutable state. We don't want to be mutating the state. Instead, we want to transform the state as much as we can. And because transforming the state becomes a lot more easier to reason and work with than mutating the state. But obviously, one question we may ask here is, oh my gosh, if you're going to be dealing with immutable state, would you not base performance by copying objects over and over and over? Well, let's think about something really in parallel here again. Version controls have been doing this for a long time. When you deal with the version control, you check in files. The version controls don't make a full copy of the files, obviously. What they do is they make very nice smart copying where they keep the differences around. So in other words, we do smart copying rather than true copying or full copying. In a similar way, languages and tools and libraries can do this for us. When we make a copy of an object, it doesn't have to be a full copy. It can be a very efficient copy. A case in point is, one example is tries, where tries is a data structure quite widely used in languages like Clojure and Scala, where tries make a very smart copy of objects minimally on copy on demand, and that becomes really efficient. Likewise, libraries can also be smart about how they handle data so they can minimize these garbage objects being created in between. So there are ways to really save performance while achieving these goals as well. But one of the most important things to think about is functions are considered as first-class citizens. So what does that really mean, functions are first-class citizens? Well, what that means is so far what we have done is we can pass objects to functions. Well, sure, we can create, in this case, objects within functions. And then finally, of course, we can return objects from functions. So we are used to doing these things for a long time. But what if we treat functions as first-class citizens? We can start treating them and moving them around and passing them around. So in other words, these are called higher-order functions. So what is a higher-order function? Well, a higher-order function typically is going to take this idea that we talked about, but in addition to doing the object composition, we can also do function composition. So if you look at the higher order functions can pass functions to functions as well, not just objects. They can create functions within functions, and of course they can also return functions from functions as well. So those become what are called higher order functions that you can work with very effectively. So we can do object composition or object decomposition, but we can also do function decomposition as well. But one of the most important things to keep in mind is that functions don't have side effects. I want to emphasize that for a minute because it's easy to miss this a little bit. So I want to emphasize that functions have to be pure. Well, what does it mean to be pure? Meaning pure functions don't have side effects. So side effects, well, what are side effects then? Well, in this case, there are 2 points we need to consider. And I would argue that the first point is a lot easy for a lot of us, but the second point is not that intuitive. The first thing is a pure function does not change anything. So we can all relate to that. Of course, if a function is modifying something, well, that's not pure. But there is an important rule here, does not depend on anything that changes as well. So in other words, a pure function should not make any changes, but it shouldn't depend on anything that changes as well. Well, the first rule, I think, is pretty clear to most of us. It's quite obvious you don't want to mess with data. You don't want to change shared data. That's obvious. But if I say that a pure function should not depend on anything that changes, we're like, why? Well, the reason is one of the critical features of functional programming is that functions can be lazy, and if you're depending on something that changes outside, your function cannot be lazily evaluated. We'll see some of this later on when we look at some examples along the way. So having said this, what are really the benefits of this? One of the biggest benefits is that it becomes easier to work with the code. It reduces accidental complexity in code quite often. That is one of the biggest benefits. But I want to draw the distinction between functional style versus purely functional programming languages. A purely functional programming language will not allow any mutability, period. A functional style language often permits mutability at the risk of we failing to do the right things. So it puts the burden on you rather than protecting you, but it provides higher order functions. So in other words, you can say if a language provides higher order functions, it's a functional style language. If a language goes to the extent of limiting mutability, in addition to providing the higher order functions, then it becomes a purely functional language. For example, Java and a lot of other languages are functional style languages. Language like Haskell, for example, is a purely functional language because they provide higher order functions, but they don't also permit mutability. But what are some of the real benefits of this? We're going to be looking at state transformation rather than state mutation. So we take the data and transform through the states rather than mutating the state. But let's look at what this really means to us in some context. Let's say, before we go any further with this, let's consider methods. So what in the world is a method? Method is a function, after all, which often belongs to a class or to an object. So that's what we call as a method in Java. A method is a function. But that function often belongs to either a class or it belongs to an object. But on the other hand, a function has 4 things. Well, what are the four things a function typically has? The first thing it has is a name of a function. So we celebrate, we give names for functions. The second thing it contains often is a return type. Well, we tell what does this function return. The third thing is a parameter list. And of course, the last thing, of course, is the body of the function. So that's what a function typically contains when we write them. So let's look at an example of using a method or a function. Suppose I were to say thread is equal to new thread. And then, of course, I'm going to say thread.start over here. And then I'm going to simply say in main over here. And we can see that in main just popped up. But of course, I want to do something in another thread. So we say new runnable over here. And then once I create the runnable, I'm going to say public void run. And then within this run method, of course, I'm going to say in another, let's say, another thread. So in this case, of course, we will run this function. And we can see that in main popped up first. And then in another thread, once that thread kicked in, it said that that's going to run. But if you look at this code, line number 16 is a method, which is the run method. We wrap that run method within runnable, and then we passed it to the thread class. We've been doing this for a very long time, of course. But imagine you are boarding an airplane, and they tell you you can only take 2 items with you, and you cannot take more than 2 items. So what are the 2 items you're going to pick from here? Well, what do you think is the most important item here, the one you cannot board without? Obviously, that would be the body of the function. Without the body of the function, there's no point doing this. Well, yeah, you selected 1 item, you got only 1 more item you can select. Well, obviously, what good is having the body if you don't have the data to work with? So you have to have the parameter list to be given to you. And that's it, you're out of limits. You can only take 2 things, and that's exactly what Lambda do. Lambda expressions essentially have only those 2 things. It's got a parameter list, first of all, an arrow that separates the body from the parameter list. That is the structure of a Lambda expression. So a Lambda expression has at the very minimum, a parameter list and a body. Well, what about the return type? The return type is inferred based on the context, so you don't have to say the return type. What about the name of the method? Who cares? When the work is done, it's anonymous. So Lambda expressions are anonymous methods whose return types are inferred, and all you carry with you is a parameter list, an arrow, and the body of the function. So what I'm going to do here is take this example right here that worked a minute ago, but I'm going to go ahead and rewrite this time. But this time, I'm going to remove all the ceremony around it. Notice that's pure noise that I've highlighted. So I remove that noise, put a little arrow right there, and then I'm going to remove the remaining noise from here. And so we converted the code to use a Lambda expression rather than using an anonymous function, anonymous method, anonymous class. So in this case, the thread is actually a constructor, which is a higher order function. The thread says, you don't have to pass an object to me of runnable. It's okay if you pass a function to me which has no name, and that function, of course, is the Lambda expression that we are passing to this function. So in this case, you can see that we passed a function which takes no parameters, and then, of course, the arrow and the body which is printing that message. So we were able to pass this method. So for the first time in a long time, we've been able to treat the function as a first-class citizen. So what that means is, it's kind of like we've been treating functions like they're kindergartners. The function comes to you, this little code comes to you and says, could I go to the neighborhood park, please? You said, no, sweetie, you cannot go alone. Let me send an adult with you, and we have been wrapping it. Now you can free that, and you can send it away on its own. So we've been treating functions as a first-class citizen now in Java 8 moving forward with the functional style of programming. So what this leads us to is we can do some really powerful things with this. Let's quickly look at an example of how we can reap some of these benefits. Let's go to what we've been doing for a very long time, which is a very traditional looping. So I got a list of numbers 1 to 10 right here. And what I want to do is loop through these. So I could say for I equal to 0, I less than, and then numbers start. And then you pause and ask, is it size, is it length, is it count? Because obviously we can't have a standard, isn't it? If it's an array, it's a length. If it's an array list, reduced its size, go figure. So then we could say plus plus, and then we pass again as the question, is it less than or equal to, because we are never sure about it. And then of course, to add insult to injury, I got to say numbers again and do a get and get the data out of it. Well, this is a very high ceremony, but if you look at this code, I'm going to argue this is a very complex code. You may say, wait a minute, did you say complex? Isn't this a simple for loop? Oh no, this is not a simple for loop. It's a familiar for loop. It's important not to get confused with the terms. The words simple and familiar are very different from each other. This is not a simple for loop. It's a complex but familiar for loop. So what is familiar? Familiar is something we have looked at several times. We don't probably care to look at it again, and something that we know very well. And this is a very familiar for loop. But I'm going to argue this is complex. In fact, it's very easy to prove it's complex because there is something already very simple. We could say int element in numbers, and then we could, of course, output the element right off the bat. So you can see that while both of the code produce exactly the same result, this one is a lot simpler than the previous one. These two collectively are known as external iterators. But we can use what's called an internal iterator instead. So what we can do in here is we can do internal iterators moving forward. And what that means is we can say, rather than iterating through this way, we could simply say, well, numbers.for each. Well, let's stop right there and talk about this for a second. Notice in the earlier example, we were passing the number to for, and we know one thing about code structures like this, they are never polymorphic. On the other hand, the minute you say numbers.for each, that you know is polymorphic because the implementation of for each can change depending on the runtime implementation of the collection you are dealing with. So that's a benefit already that you are carrying with you. But what we can do with this is you can now say for each, and then you can say new consumer integer. And then of course, in this case, I'm going to say public void accept integer value or element e, and then we could output this element right there. So in this case, you can see the output is exactly the same as before. We didn't have to use an external iterator. We used an internal iterator. Now, the benefit of this code is you are telling what to do and not how to do it. You're focusing on what to do per iteration. You're putting the iteration on autopilot. And of course, you can enjoy polymorphism. All of these things are good things. But I know what you're thinking. You're thinking, if all that is really good, but to reap that benefit, if I have to use yet another anonymous inner class, heck no. Well, sure. But that's the beauty of this. We don't have to. We can take this one right away and say, well, rather than working so hard, we can remove all the ceremony from here, only keep the essence out of this, and then we can remove the rest of the part as well, and you can see the code still works right here. So what we can do in this case is we can get rid of all that noise in the code. These are called functional interfaces. I always chuckle when I hear the word functional interface because I wonder if there are some interfaces that are functional, what about the other ones, are they dysfunctional? But in essence, basically in this case, wherever a single abstract method interface is expected, your callables, runnables, the consumer in this case, file filter, anywhere a single abstract method interface is expected, you can now pass, of course, a Lambda expression very easily. That's what we just did. But we can go a step further and improve this even further, if you will. Now look at this code for a second. We are saying, here is a Lambda, given an integer, I'm going to go ahead and print that integer. But let's take a wild guess. If you are iterating over a collection of integers, you put your hand into this collection and pick an element in your wildest imagination. Can you imagine what you would pick from a collection of integers? A dog? A monkey? Well, of course it will be an integer. So you know it's an integer. The language knows it's an integer. Why bother saying what the type is? So for the first time in a long time, Java is finally intelligent. We can use very easily type inference with Lambda expressions. So you can simply leave out the type because the type is not adding any value in this case. It is very obvious. Now make no mistake, this is not dynamic typing. This actually is static typing where the type is inferred at compile time. Just to verify that, if I go back to this code and on the element E, if I were to call foo, notice the error message we are getting. It says method foo, variable E of type integer, and so it very clearly knows that E is of integer. There is absolutely no confusion in this point, so we don't have to really specify the type in this case. But we can go a step further again in this, if you will. Now that we know that this is an integer, we don't have to say the type. Well, we can also get rid of that silly parentheses. So if you only have exactly one element being given to your lambda, you can get rid of that type, the parentheses as well. So if you don't have any parameters, you have to put a parentheses. If you have two or more parameters, you have to put a parentheses. But if you just only have one, you don't have to really specify that. But one more improvement. If you look at this code that we have at hand, notice that in this case, we receive an E and we print it. And we could have done E plus 1, for example, or we could have done E times 2, for example. But the point is, we didn't. And all we are doing is receiving the data and simply passing it. And this kind of lambda is extremely trivial in that it receives an argument, a parameter, and either passes it down to another function or invokes a method on it. I got a special name for these kinds of lambdas. I've called these lambdas as the office space pattern. If you remember watching the Office Space movie, hey Tom, what do you do in this company? I take the requirements from the programmers and I give it to from the manager, from the business people, and I give it to the programmers. So all that Tom was doing in this company was he was taking the requirements from the business people and giving it to the programmers, effectively really no purpose. Well, when you have a lambda which is not doing really a lot other than simply transforming the data, you are going to get tired writing this. And you're going to say this code is stupid. But history has shown one thing to us. Java programmers never write stupid code. They instead develop IDEs to vomit stupid code, and people will be asking each other, what's that IDE shortcut you're using to do this? Well, they knew this was coming, so they removed this duplication. So if you notice, we have an E over here. So this E is common, so we'll remove it with this E right here. And then we'll remove this arrow as well, and we simply change this dot to double colon, and these are called method references. Method references make the code a lot easier to understand and work with. I'm going to say method references take a little bit more effort to write them before you got used to them, but method references often are easier to read. So they are easier to read than write in the beginning, but over time we get really better at it as we use it. So what we did in this example is we took an external iterator, the one that we had before, and we refactored it a few times. Here is the traditional external iterator that we started with. We got something simpler, which is also an external iterator. Then, of course, we took the internal iterator, which was verbose, but showed us how we can do the looping and print stuff inside this loop. And then finally, of course, we traded that with lambda expressions. We got rid of the type and used the type inference. We got rid of the parentheses after that, and then of course eventually we used a method reference because this particular lambda was that simple. So this gives you an idea about how we can go about using lambda expressions to start writing these kinds of code moving forward. So this becomes a very fundamental shift in how we do this, but one of the things to keep in mind is this is essentially a way of programming where we favor more of a declarative style of code than first and then a functional way of doing. So what is declarative style? A declarative style of coding is where you tell what to do and you let the underlying functions figure out how to do it. In an imperative style of code, you spend your time and effort telling what to do and also how to do it. Let's look at one example of this to get a better feel for what that really means. So here is a list of numbers 1 to 10, but let's say the given problem is find the total of double of even numbers. So we were asked to find the total of double of even numbers. So what do you normally do to create this in the imperative style? Well, first of all, you would say result is equal to 0, and then when you're done, you want to print out the result. But then you say over here, for int element coming from numbers, and then you say if element mod 2 is equal to 0, then of course you're going to say result is equal to e times 2, but then you have to put a break out of it to break out of this loop. Well, in this case, of course, well, actually, in this case, we want to find the total of all the numbers, so no break here. So we got to make all these decisions, and then we have to say plus equal to, so you can run through it. Well, in this case, of course, total of double of all the even numbers in the collection, but we have written code like this forever. But if you look at this code, anyone here has written code like this before? Well, of course, every one of us. But the question is, how do you feel when you write code like this? Dirty, right? Really dirty. In fact, after a day-long work, after writing this code, you go home, and the kids come running towards you. You say, don't touch me. I got to go shower first. Because this is very low-level coding we have to be doing over and over. We can do this again, but before we do this, let's talk about two different things, two different smells of imperative code. The first smell is we got a variable we defined over here, but we are mutating that variable over and over and over. That's one of the smells of imperative style of coding, is we do mutability quite often. The second thing is you had to spend your effort telling not only what to do, but also saying how to actually do this. Well, on the other hand, we can rewrite this code this time, but I'm going to say output. We'll start with numbers over here, dot stream. Think of stream as an internal iterator. And then we can say filter, and I'm going to say given an element E, return the elements only that are even and not any of the other elements. So in this case, we applied a filter. We do a map given an element times 2. And of course, finally, I'm going to say, go ahead and give me a sum operation on the elements results and return the result to me. Well, if you look at this code, both of those code produce exactly the same result. But there is some really key differences between these two kinds of code. The top code is, of course, imperative in nature. We tell what to do and how to do, and we also have mutability in the code. If you look at the code in the bottom, I'm going to say the code in the bottom is very humane. No variable was tortured in the making of the result. So we're not mutating any variables repeatedly. The second thing is, if you look at the code in the top, you had to say every single detail. You had to say, get one element at a time, please. Check if that element is an even. Go ahead and double that element right here. Then fetch the current value of result. Then add to the value of result. And then store it into the result. You had to say every single thing. This code is like talking to a toddler. Well, the first time you talk to a toddler, it's very exciting. You're going to say, wow, this was awesome talking to the toddler. Well, the next day you realize you got to say the same thing over and over. You're going to say, well, walk slowly, hold it with both hands, look where you're going, don't step on that cat on the way. You're going to be having to say this. And then you realize this is going to go on for the next 18 years. That's called parenting, isn't it? Well, that's how it feels when you start writing code with imperative style. On the other hand, the functional style feels like you're talking to a responsible adult. That is one of the biggest benefits you get out of this, is a very nice way to transform. So given a collection of numbers, get me the collection which is only even numbers, double the values and total, so the code begins to read like a problem statement. It removes the accidental complexity that usually is inherent in code. That's one of the biggest benefits you get. So what are some of the differences? In the imperative style, you focus on how to do things, whereas in a declarative and functional style, you focus on what to do mostly. You encourage mutability in an imperative style. You transform data in functional and declarative. You often deal with side effects when it comes to imperative style. You write pure functions when it comes to declarative and functional. Notice each of these functions are pure. They don't change the world around them. They are not dependent on anything that's mutable. That's what these do along the way. And of course, you pass objects. In this case, you can pass functions as well. And then finally, the code is very hard to compose in imperative style because statements often cause mutability, and you got to go back and get the data, whereas functions nicely compose, and you can transform data from one to the next to the next to the next. But I want to deviate a little bit from this and talk back into functional style about lambdas and closures for just a minute. So going back to this example, let's take values 1, 2, 3 for a minute. And in this case, what I'm going to do is I'm going to ask for the values to be doubled, first of all, and printed. So in this case, I'm going to say numbers.stream. And then I'll say map given an element times 2. And then for each, I'm going to say system.out and println. Well, looking at this code for a second, look at this line alone, if you will. Here is a lambda. If I ask you what 2 is a literal, of course. What in the world is E? E is a parameter to the lambda. Much like args is a parameter to main, E is a parameter to this lambda expression. Well, this lambda is very self-contained. It's happy, it got everything it needs, not a problem. On the other hand, if I were to say factor over here, well, if you look at this code, if I ask you what is E, it's very clear what E is. E is the parameter to this lambda. But what in the world is this factor? Well, the factor, of course, is not defined within this lambda, so this lambda has to look for this factor. So this lambda, well, I'm going to put this down here. So this lambda has to close over its defining scope. So defining scope, looking for the variable factor to bind to. So in other words, this lambda has to close over. Try saying the word close over really fast several times. Now you know what a closure is. So a lambda does not have state. So I'm going to say lambdas are stateless. On the other hand, what about a closure? Closure has immutable state. And so you want to make sure that it's actually immutable. That's very critical. So closures carry a state with them. Lambdas are pretty stateless. And so what a closure can do is a closure can capture a state where you are defining it and carry it over to the point of execution. Which may be looking at this code, but let's quickly take a look at this right here. This lambda is defined right here in the main. Then you call the map method. Within the map method, you could either call the lambda or you can pass the lambda down a few more levels and you may call the lambda after that. So in other words, the lambda that's defined in the main may actually get executed at 1 or 2 or 3 levels from below the stack, but when it's executed in that stack level below, it needs a variable defined up here, so that is where it captures the context from here and carries it down there for availability. So that is basically what a closure is. So one of the things we should keep in mind is closures carry state, but it's important for us to make sure that the state that is carried by the closures are immutable. Now, why is it so important that the closure states are immutable? Well, to understand that, let's go ahead and do this a little differently. I'm going to go ahead and bring in the stream over here. So I'm going to say stream.stream, and I'm going to say stream of integer right here, and then is equal to numbers.stream. But I'm going to say dot map, given an element, I'm going to say element times factor. And then, of course, in this case, I'm going to say that given the stream dot for each, I'm going to go ahead and say system.out and println, and I'm going to go ahead and print this string. Well, that's good so far, but where is the factor? I'm going to say in this case, this factor is int factor is equal to 2. So the code actually in this case is taking the factor and making a product out of it. So that obviously worked, but one thing to keep in mind is, look at this closure for a minute. Well, this closure definitely is not modifying any particular variable, so that is good. It satisfies the first rule of purity. It doesn't change anything. What about the second rule of purity? Remember, the second rule of purity is it doesn't depend on anything that changes. Oh, wait a minute, it does depend on factor, but one of the beautiful things about Java is that it treats these as what are called effectively final. So in other words, you could put the word final right here. In this case, if I say factor equals 4, notice you get an error right there on line 15, and it says you cannot change factor because it's final. But what if I remove this final from here? Well, in old versions of Java, until Java 7, you had to put final. You have a local variable which is accessed from within an inner class. Java 8 changes the rules just a little bit. In Java 8, you don't have to put final. Now you may say, wait a minute, Why don't I have to put final? Well, Java 8 says, you and I have been going out for a long time. We can trust each other just a little bit. So as long as you know how to behave, you don't have to go through the ceremony of putting final. So as a result, when I write this code, this is called effectively final. However, if you come here and say factor equals 4, immediately Java screams and says, I thought we had an understanding between us, and you are now violating that contract. This is why it's called effectively final. In other words, you cannot access a variable, a local variable, if you are mutating it. Well, this is a good news. This is when Java is trying to protect you in this case. Languages like Haskell are purely functional languages. There is no assignment. If you tried something very similar to this in C# or JavaScript or a few other languages, those languages will not stop you. Java is trying to be protective here and says, no, 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 don't do that. That's not a good programming practice. Don't do that. Well, that's a good idea so far, but you know how some programmers are. They will roll up their sleeves and say, let me tell you how to really cheat Java. These are very dangerous people usually. But what you can do potentially in this case is, because Java doesn't allow you to change factor, you may get tempted to say, int square bracket factor equals new int, and then you could put a 2 right here. At this point, Java is going to say, good luck and be quiet. So when you run this code, of course, you got factor 0. But if I go back here and say factor 0 is equal to 0, notice in this case, Java will no longer complain. Java will probably sit there and keep laughing and say, this is going to be fun watching this code. But in this case, it won't protect you anymore. This is also true if this was a member variable, a field in your class. Java is no longer going to protect. However, keep in mind, this Lambda, this closure is a bad closure because it's no longer pure. Why is it no longer pure? Because remember the 2 rules of purity. A pure function should not change anything. That's good. But a pure function should not also depend on anything that changes. Well, clearly, this depends on something that changes. In fact, the reason this is really a terrible code is you can take this code, make a photo of this, and show it to different people and ask them what's going to be the output. I bet you're going to get different answers from the people. And some of them will tell you, well, because factor 0 is 2, this is going to be the double of the values. Other people may say, because factor is 0 now, it's going to be 0, but which one is it? The right answer is, should we really be doing such programming? Because if you are trying to write code like this is hard to reason, error prone, very difficult to work with. This is also known as bad idea, so don't do this. So this is the reason why the purity of functions is so important. We don't want to be messing with things like this. We want to preserve the purity of closures. That becomes extremely important. So we shouldn't mix the impurity with these. But this also illustrates the point about lazy evaluation. So let's talk about lazy evaluation. I got an entire talk on lazy evaluation tomorrow, but I'll simply merely scratch the surface right now. Notice that on line 13, we had a lambda expression sitting on line 13. That lambda expression on line 13 did not execute right now as you walk over line 13 during execution. Instead, it waits until you come to line 17, and that's when that line 13 is executing. That is lazy evaluation or deferred execution. It says, I don't need to be doing this now. Well, functional programming cares a lot about this. So I'm going to go ahead and say here, if somebody comes to you and says, are you a fan of object-oriented programming? You say, oh, I love object-oriented programming. Well, why do you care so much about object-oriented programming? Well, don't get me wrong. Things like abstraction and encapsulation are extremely important. But you're not programming an object-oriented system just for abstraction or encapsulation. The real power of object-oriented programming is polymorphism, after all, isn't it? So polymorphism is to object-oriented programming. So in other words, this is what we really are after. Now, we all can agree You cannot enjoy polymorphism without abstraction. You cannot enjoy polymorphism without encapsulation. But polymorphism is what we really are after, and abstraction and encapsulation really make that possible. So polymorphism is to object-oriented programming like, and I'm going to say lazy evaluation. Evaluation is to functional programming. Now, of course, if you're going to have lazy evaluation, you cannot have lazy evaluation without immutability. That's exactly what we saw in this example. Because what does immutability do? Immutability says this function will not modify anything, and it is not depending on anything that will change, so you can run it now, you can run it later, or never run it at all. Well, if it is an impure function, you are urgent to run it. You're going to say, run it fast, run it now, before the world changes, and you're going to be in a hurry all the time. And you ask the question, when did this run? Did it run before the change or after the change? You can completely defeat the purpose. So you cannot be lazy without having immutability. And laziness is an extremely important thing, because laziness leads to efficiency in code, because you're not sitting there and making copies and copies of objects. You can defer execution until a much later time and have those executed very nicely. That's one of the biggest benefits you get out of this. So to wrap this up, one of the real powers in this is laziness, but with laziness also comes this ability to do what's called function pipelining or function composition. Function composition is a very powerful pattern. We saw examples of this earlier, but let's revisit this. So suppose I had a collection of numbers with me, let's say collection of numbers 1 to 10, and I want to this time say get the double of square root of, let's say, of even numbers. Well, I can write this in a very nice flowing pattern. So what I can do is I can say output, but this time I can say numbers.stream, and then I can say, well, filter, given an element, give me element mod 2 is equal to 0. Then I can say dot map, and math square root. After all, I'm interested in finding the square root of these. And then, of course, this is going to be mapped to double this time. And then finally, I can say dot sum. And then, of course, once I total it, I can simply return it. Well, if you look at this code this time, though, what we have done in this case is we are saying, given the collection of numbers, get me only the even numbers, but give me the square root of those even numbers, and then find the sum of it. And you can see how this begins to flow through. This becomes what's called the function composition. You go through transformations. You take the collection, you transform to even numbers to map to double to performing the sum. Well, this is a function composition, but the evaluation is also pretty lazy. So what I mean by the evaluation is lazy is, until you hit the sum operation, these operations are not going to execute, and then minimally they're going to execute whatever is necessary, so the efficiency is baked in. Furthermore, in languages like Java, one of the cool things about this is it is not taking a collection and creating an intermediate collection and then yet another intermediate collection. It's not going to be doing that for you. Instead, it's very efficient in knowing that these intermediate collections are really not needed. First of all, they're not available, they're not visible outside. So internally, it doesn't waste performance by creating all those garbage collections internally. It directly gets you to the result in the end, so efficiency is baked in. It is really hard for it to be efficient without laziness as well. In fact, when the terminal operation sum is called, that's when it performs the operation, and because of that it can be efficient. It is not wasting its time and effort building all these intermediate results along the way that you get out of this. So the benefits of doing this is, first of all, you get code clarity. When you look at the code, you're not going back trying to figure out what this code is doing. You're able to just follow this code. Think about this for a minute. If I give you a for loop with an if condition and a break and a continue, and I give you this code and ask you, tell me what this code is doing, and here's a challenge for you. Give an imperative code to somebody, to ask them what does this code do, and sit in front of them and watch their eyeball. and their eyeball is going to do this. It's going to start in the top, look at the code, and it's going to do this, and then it does this. That point is called point of confusion, right? It's like, I don't know what this code is doing. But look at the functional code. You go through a single pass through it. Given the collection, get me all the even numbers, find the square root of them, and total, you're doing a single pass through it. That becomes very clear to understand. You also have fewer errors in code because A, the code doesn't have accidental complexity in it. Second reason why there are fewer errors is there is less mutability in code as well, and that reduces errors also. So less complexity, less mutability favors a fewer errors in code. It also removes all the extra garbage variables we have to carry around, and so it becomes hard to reason. You can remove that as well. And finally, the code becomes easier to parallelize as well. If you are taking an imperative code with shared mutability and you tell them to make the code concurrent, that's really hard because structure of the code changes a lot between sequential and concurrent. On the other hand, with this kind of code, imagine this was a fairly large collection. What you can do is when you run the code, you can see that it produces the result, but you can simply throw a parallel in here, and this will run in parallel and produce the result across the course. Either you can call parallel like this, or you can turn this into a parallel stream as well. But the beauty of this, more important, is the code structure is not different between sequential and parallel. The code structure for the first time in a long time is exactly the same between sequential and concurrent. That's a huge benefit for us to enjoy, and that is one of the biggest benefits. To summarize, functional programming removes accidental complexity from our code. Well, clearly we can all agree functional programming takes a lot more effort to understand in the beginning. That's because we're not familiar with it. We are familiar with imperative style of programming. But once we become familiar, it takes us a lot less effort to write it. It removes these accidental complexity. It makes it easier to reason the code. It makes it easier to parallelize the code. So all that benefit we can enjoy. That's one of the reasons why we want to favor this. And it's really cool that most of the mainstream languages today are providing this, including Java 8. If you're interested in downloading the code examples I showed you, you're most welcome to download them at the link that's shown in the bottom. Hope that was useful. Thanks for your time.